Have you ever looked at a shiny chrome bumper on a classic car and just marveled at its mirror-like finish? Or perhaps you've noticed the lustrous gleam of a silver-plated spoon catching the light just so. That brilliant shine, that seemingly perfect surface, isn't always what it appears to be. Often it's a whisper-thin layer of one metal artfully laid upon another, a kind of metallic alchemy made possible by the fundamental forces of the universe. This transformative process, where we use electricity to coat an object with a metallic skin, is called electroplating. It's a quiet hero in our daily lives, giving strength and beauty to countless objects we see and touch. Humble coin in your pocket, sophisticated circuitry inside your smartphone. It's a story of atoms on a journey, guided by an invisible current. Think about it for a moment. The universe is governed by laws, by the predictable behavior of particles and energy. Electroplating is a beautiful, practical application of these very laws. We take something ordinary, perhaps a piece of steel or a plastic component, and we give it the properties of something far more precious or durable: gold, silver, chromium. This isn't magic, it's science. Convincing them to leave their solution and deposit themselves one by one onto a new surface. This process makes things more attractive. Yes, but it also serves a deeper purpose. It protects materials from the relentless forces of corrosion and wear, extending their lifespan and enhancing their function. The core idea is astonishingly simple when you break it down, yet the results are profound. Electroplating is the act of using an electric current to deposit a dissolved metal onto the surface of another object. It's a controlled electrochemical reaction that allows us to engineer surfaces with specific qualities. We can make a weak material strong, make a dull object brilliant, make a reactive surface inert. This ability to manipulate matter at the atomic level is a testament to our understanding of chemistry and physics. We're not just painting on a layer of metal. We are fundamentally bonding it to the object, creating a new composite material combining the core strength of the base with the surface properties of the coating. This process is happening all around us, often unseen and unappreciated. That golden sheen on a trophy isn't solid gold. It's a delicate electroplated layer on a cheaper base. The durable, corrosion-resistant coating on nuts and bolts that hold our world together is often zinc, applied through electroplating. So, how do we command these atoms to perform their dance? The process of electroplating, at its heart, involves a simple circuit and a special bath. Imagine a tub filled with a liquid solution. This isn't just any liquid, it's an electrolyte, which means it contains dissolved metal salts. These salts break apart in the water, releasing positively charged metal particles called ions. If we want to plate an object with silver, for instance, our bath will be teeming with silver ions. This solution is the stage for our atomic performance. Now, we introduce the main actors. First, the object to coat, a brass key. The key is connected to the negative terminal of a power source, like a battery or a rectifier. This makes the key the cathode, the destination for metal ions. Then, a pure silver bar is placed in the bath. The silver bar connects to the positive terminal, making it the anode, the source of ions. With everything in place, we flip the switch. The power source sends an electric current flowing through our circuit. Before any atom can find its new home, the stage must be perfectly set. The single most critical step is surface preparation. Think of it like painting a wall. If the surface is dusty, greasy, or covered in old, flaking paint, the new coat will never stick properly. The same is true for electroplating. The object to be coated, known as the substrate, must be immaculately clean. Any trace of oil dirt rusts the natural oxide layer that forms on metals when exposed to air will act as a barrier, preventing the new metal layer from forming a strong, permanent bond. This would result in a coating that could easily peel, flake, or blister. To achieve this level of cleanliness, a multi-stage cleaning process is employed. First, the object might undergo a physical cleaning, like sandblasting, polishing. This is followed by a series of chemical baths. While the high-tech electroplating we know today feels distinctly modern, the idea of coating one metal with another is surprisingly ancient. The universe has been playing with these principles for a long time. Archaeologists have uncovered artifacts like the so-called Baghdad battery, dating back over 2,000 years. While this is debated, artisans in ancient civilizations developed sophisticated methods like fire gilding using mercury to apply a thin layer of gold. These early methods were dangerous and inefficient, but they show a timeless human desire to bestow precious metal qualities onto common materials. The scientific breakthrough that paved the way for modern electroplating came in 1800. Alessandro Volta invented the first electric battery. His voltaic pile provided a continuous electric current, the engine needed for electrochemistry. Just a few years later, in the 1800s, scientists began to experiment in earnest. Luigi Brugnatelli, John Wright, the Elkington cousins. They learned to use Volta's current to move metal ions through a solution, developing the first cyanide-based baths for plating silver and plating gold. This was a revolution. Suddenly, the growing middle class of the Industrial Revolution could afford silver-plated tableware and gilded decorative items that looked like solid silver and gold. Today, electroplating goes far beyond making things look pretty. In electronics, electroplating is fundamental. Printed circuit boards are copper underneath, often plated with a thin layer of gold, or plated with tin to prevent corrosion and ensure reliable electrical connections. Without electroplating, the miniaturized electronics powering our computers, phones, and satellites simply wouldn't be possible. It enables the flow of information in our digital age. Electroplating is a champion of durability and efficiency. In aerospace and in automotive industries, components are plated with hard chromium or nickel to resist extreme friction, high temperatures, and corrosive environments. A thin layer of a high-performance metal can protect a critical engine part or a landing gear component, dramatically increasing lifespan and ensuring safety. This process also has environmental benefits. Coating an inexpensive base metal like steel with a thin protective layer of a corrosion-resistant metal like zinc or nickel makes parts last longer, reduces replacements, and conserves resources. It's a way to get maximum performance with minimal material.